Good afternoon. Today our group would like to take some time to discuss our senior design project, Project Lightbeam. Our group decided to set our focus on the themed entertainment industry as it is an industry we all respect. Additionally, one of our members currently interns at one of the major companies in this industry, which allowed us to get a deep dive into our topic. The goal of our project is to create a model coaster that would allow us to demonstrate the functionality of large-scale coasters and allow users to interact with the coaster as if they were operators for a large attraction. This is our team. I'm Amy Largo and I'm a computer engineering major.
I'm Mohammed Ali and I'm majoring in computer engineering.
I'm Besnil Deeb, and I'm also a computer engineering major.
And I'm Nassim Elaham, also computer engineering major. So to begin, we'd like to discuss the motivations behind our project. Based on experience in the industry, we have learned that testing out systems can be extremely time-consuming. With having a small-scale model to test ride control systems ahead of time, we can save a company time and future resources during downtimes. Additionally, from a theme park enthusiast perspective, having a training tool to allow us to gain hands-on experience will allow us to learn the necessary skills for becoming skilled control engineers. Additionally, in today's markets, hands-on PLC training and ladder logic training is not accessible to students, making it difficult for external parties to learn about control systems.
Therefore, the goals of our project is to create a small-scale model roller coaster that can be controlled by an operator console similar to current operations in today's theme parks. Our goal is to follow the same level of safety and logic behind roller coasters, such as block zones, which will be explained in later slides. Along with safety in mind, one of the team's objectives is to also create a model that follows relevant industry standards while being affordable and replicable.
Here are the engineering requirements for our project. Highlighted in yellow are the requirements that the team has decided to demonstrate. The ability to demonstrate safety block zones, safe stopping distances, and initiating motion at a safe speed is the primary focus of our project.
In the block diagrams shown on this slide, we outline the major components of the model. The main key components to highlight in our project is the LED strip, which will simulate the vehicles along the track, LED indicators that indicate a brake will be activated, and the photoresistor sensors, which will allow us to detect which zones the vehicles are detected. Here is the block diagram for the ride control logic. The logic demonstrated in the diagram is similar to functions used in actual coasters. Notice how the system is designed to check for several things prior to allowing motion.
Here we have an illustration of our operator console. The operator console will consist of 5 buttons and a key switch. The buttons are as follows. An emergency stop button to stop all motion in the coaster and bring the model to a safe state. A station stop button to inhibit any vehicles from entering or leaving the station. A dispatch button and enable button. The dispatch button will allow a vehicle to leave the station as long as the MCU receives a signal from the enable button. And finally, a reset button to allow the operator to reset a station stop or emergency stop and resume motion. There will also be a key switch that allows the operators to provide power to the coaster. An LED indicator will also be used to determine if the model is currently powered. The illustrations on the right outline the block zones and the equipment locations for the roller coaster.
In order to control the roller coaster, our team considered different microcontrollers to help us achieve our desired design. Our requirements for the MCU was its compatibility with our chosen LED strip libraries and adequate GPIO pins to support our project. The first microcontrollers that we looked at were the Arduino family of controllers. These controllers stood out to us as they had a higher capability with all LED strip libraries and allowed for low-level commands which were beneficial to our case. The Arduino microcontrollers also stood out to us as they can run at 5 volts or 3.3 volts, which allowed for flexibility in our power designs. The team also considered the Texas Instruments microcontrollers due to our previous experience with the boards. The TI boards featured lower power modes and more flexible PWM controls, which was enticing to our team. Last but not least, we had also considered the STM32F407 VG board as it contained an ARM based chip with the high capability to run advanced algorithms. Since our requirements were to have ample amounts of I/O pins and to be affordable, we decided to go with the Arduino Nano as it had 2 additional analog input pins than the Arduino Uno.
To simulate the vehicles around the track, we will be using an LED strip. On the track, 4 LED pixels will be the length of one vehicle, and the LEDs must be bright enough to be detected by the photoresistor sensors. For our project, we had 4 options that we looked at: the WS2812B RGB chips, 5050 RGB LED chips, the 1138 digital RGB chips, and the SK9822550 RGB chips. From our options, we immediately eliminated the 5050 RGB LED chips as they can only be controlled in groups of 3, despite having the ability to display colors more than regular RGB lights. Our project requires us to control the LEDs individually and to control the brightness for each LED. Additionally, we eliminated the SK9822550 RGB. As shown in the table, we decided to go with the WS2812B RGB LED strip as its ability to adjust the brightness of each pixel enticed us. Additionally, the WS2812B RGB operated at 5 volts, which was also in line with our requirements for safe touch voltage. As compared to the other LED chips, although it was the most expensive one, we felt comfortable as a team with our decision due to the amount of positive reviews from active LED strip users and due to how easy making modifications to this specific LED strip would be.
The next major component in our project is the operator console and its peripherals. Planning whether buttons on an operator console should be normally closed or normally open is a critical aspect of designing control systems, particularly in industrial and automation settings. This decision directly impacts the safety, functionality, and reliability of the system. Determining which state, whether open or closed, a button should default to when unpressed allows engineers and operators to establish the system's standard behavior during regular operation in emergency situations. The choice between normally closed and normally open configurations should align with the specific requirements of the process. For instance, critical emergency shutdown buttons are often designed to be normally closed, ensuring that the circuit is broken and the system halts when the button is pressed. On the other hand, typically open buttons may be suitable for routine start and stop functions. This careful planning minimizes the risk of accidental errors, enhances operational efficiency, and promotes overall system safety and control.
With this in mind, our team carefully selected specific contacts for each button and the key switch. For the enable button and reset button, we chose a single normally closed contact. For the dispatch button, we used a single normally open contact. As for the emergency stop and station stop, we chose to have dual normally closed contacts for both buttons. And last but not least, for the power key switch, we ensured that the switch we selected had both a normally closed and normally open contact. In today's coasters, the buttons used on their consoles are industrial buttons from Allen Bradley, which can easily cost from $60 to $100 each. Due to the budget of our project, we opted to purchase our buttons from third-party sellers that produced high-quality buttons for a low price but are not rated to the same extent as the Allen Bradley ones. Our buttons cost us about $10 each, and we were thoroughly tested after receiving them.
The next technology we needed to look at was the type of sensors used for our project. Since the vehicles will be differentiated from each other by the brightness and color, our sensors needed to be able to detect the difference in brightness. Our options consisted of the photoresistors, photodiodes, and phototransistors. When deciding which technology to go with, we had to keep in mind the type of data we would be using the sensors for. Photoresistors piqued our interest for its high sensitivity to visible light, which was perfect for our application, whereas the phototransistors also had a high sensitivity to all types of light except for low light. In the end, our group decided to go with the photoresistor as it was more cost efficient than the other options. Additionally, Our group has had previous experience using photoresistors to detect lux values in other projects and felt comfortable using them again. Another reason why we chose the photoresistors was its short range. Since these sensors were to be positioned directly along the track, we wanted the sensors to only operate in a shorter range to eliminate any external noise and or input from outside light sources.
Due to the large amount of input and outputs in our project, we ran into a design issue of expanding the I/O pins on the MCU. Therefore, one of the solutions we made was to connect either a multiplexer or shift register to the Arduino. One of our project requirements requires us to process the data from our inputs quickly. Therefore, processing time and the amount of pins were the major deciding factors when selecting our I/O expansion method. In regards to processing time, the multiplexer had a faster processing time than a shift register and was able to handle both analog and digital I/O. Shift registers, on the other hand, can only handle digital I/O, but use less pins on the Arduino. Based on the specifications from each method, our team decided to use a multiplexer due to its simplicity and ability to handle the variety of I/O that our project will be using.
For the software portion of our project, our main goal was to follow the logic and functionality found in programmable logic controllers, which are used in today's coasters. These programmable logic controllers are programmed using ladder logic. Since programmable logic controllers are expensive and only available to specific consumers, we opted to mimic ladder logic through the Arduino. Ladder logic is a graphical programming language used primarily in programmable logic controllers, or PLCs, to control and automate industrial processes. It operates on the principle of representing control logic as a series of interconnected rungs similar to a ladder. Each rung consists of input contacts which represent sensors or switches connected in series or parallel fashion. These input contacts are evaluated based on their status, such as open or closed, and the evaluation propagates from left to right along the rung. If all conditions on a rung are met, it activates an output coil, which controls an output device like a motor, valve, or indicator. An example of ladder logic for an emergency stop button is shown. In terms of our project, the input contacts and output coils will be represented by variables declared in the code. The Arduino will maintain the states of the variables and update them accordingly based on the input received from the buttons.
In Project Lightbeam, we will also be following block zone logic, and we'll use the photoresistor sensors to differentiate the zones. Block zones on a roller coaster are designated sections of the track that are strategically placed to ensure safe and efficient operation of the ride. These zones are equipped with sensors and brakes to control the movement of roller coaster trains. The primary purpose of block zones is to prevent collisions between trains by maintaining a safe distance between them. Each block zone can only accommodate one train at a time, and they are separated by brake runs or other mechanisms that slow down or stop the trains. This system ensures that only one train enters a block zone at a time, preventing accidents. The diagrams on this slide outline the locations of the sensor relevant to the track and provide another example of how ladder logic is used to control vehicles.
This diagram outlines how the Arduino will manipulate the input variables and control the outputs on the LED strip. One of the important variables to note is the block zone state and the vehicle position, as these other variable states are also dependent on them.
As previously mentioned before, the main hardware components involved in our project are the LED strip and the photoresistor sensors. Each of these hardware components needed to be strategically placed in such a way where the vehicles can be detected in the expected locations. On the diagram, the green circles represent the locations of the sensors, while the pink sections and red squares represent locations of equipment that are controlled by the brakes and the chain.
Here are the final locations of the hardware on the model. As you can see, we have the photoresistors along the track at the end and beginning of each zone. Additionally, we have individual LEDs lined up where the brakes should be located. At the end of the track, near the station, we have our operator console and PCB that houses the components that make our coaster run.
Our project's power flow diagram displays an organized and efficient power distribution. It shows how power is distributed from the power supply to the DC to DC converter to the Arduino microcontroller. The power supply delivers 30 volts and 5 amps. It is the primary source of our electrical power. Because we need to meet the voltage needs of the other components, we have included a 2-channel DC to DC converter with 3.3 and 5 volt outputs. These output voltages can be chosen based on the specific voltage requirements of the different components. It then connects to the Arduino Nano microcontroller, which serves as the primary unit for our system.
This is the PCB schematic that was used to design our PCB. In this schematic, we have two 16-channel multiplexers connected to an Arduino microcontroller. All 29 of the inputs and outputs are shown in the schematic through the connection of the wires. As seen in the figure, the buttons and LED indicator are modeled with boxes with pins, which will be connected to the physical components after the PCB is printed. Resistors between components were added to limit current. This was calculated during the testing phase to ensure the proper value was placed in the design.
This is the PCB assembly after running the PCB schematic into AutoCAD Eagle. However, we had to manipulate the components and change it so no errors occurred. This PCB design is 80.01 millimeters by 100.33 millimeters, which translates to about 3 by 4 inches. Throughout the design process, we manipulated the arrangements of the components and routed the traces cautiously. We ran multiple DRC checks to confirm that no errors were happening when designing the PCB assembly. This is the final PCB assembly with no errors. The PCB will house the Arduino microcontroller and the multiplexers, which will then run to the equipment throughout the track using long cables. Here is the final PCB layout with the components soldered on the board. Each component has been tested for continuity and for overall functionality. As you can see, one of the changes made to the PCB layout was the addition of a power module. This power module takes in a DC input and converts it to 5 volts, distributing it across the traces to the end components.
This hardware schematic is a representation of electrical components and connections that show how our project will be set up. This schematic displays how the two 16-channel multiplexers connect to the Arduino microcontroller, whilst also showing the connections of the inputs and outputs. The components that are displayed in this schematic are LED strips, 14 photoresistors, LED indicator, 7 individual LEDs, 5 buttons, and 1 switch. With the two 16-channel multiplexers, we are getting a total of 32 pins, which is beneficial for our wiring setup. This enhances our capability of being able to connect a variety of inputs and outputs on the Arduino microcontroller. To connect each multiplexer to the Arduino microcontroller, it is important to know that the multiplexer needs to be connected to 4 digital I/O pins and 1 analog pin on the Arduino. For the first multiplexer, labeled 1 on the schematic, we have the pins I8 through I13 all taken by the 5 buttons and 1 switch. On that same multiplexer, we have the analog pins I0 through I6 taken up by the 7 individual LEDs, which is labeled number 7 on the schematic. For the second multiplexer, labeled number 2 on the schematic, we have the pins I2 through I15 all taken by the 14 photoresistors that need analog input pins that are given by the multiplexer. The Arduino microcontroller is also connected to the LED strip and LED indicator on pins D10 and D11 respectively.
Here is the final model. As you can see, we were able to fully construct the model to accurately match our designs and effectively place the equipment along the track.
For our budget, so as a team, we have spent about $450 purchasing the parts for the project, and the details of this are outlined in our bill of materials. Here is our work distribution. The work distribution was determined based on each team member's strengths and weaknesses. The project team aimed to divide the work evenly to ensure fairness throughout the project and to also ensure that each part of the project has been handled appropriately. And with that, that concludes our presentation.